Uh, Question number 5. Part of an electric circuit is shown in Fig 5.1. The circuit is used to produce half-wave rectification of an alternating voltage of potential difference PD Vin. So the voltage labeled Vin applied across these two terminals is the input voltage Vin. The output voltage across the output PD across the 14 kilo ohm resistor is V out. So the voltage as measured across this output resistor is equal to V out. A component is missing in the circuit of Fig 5.1. Complete the circuit diagram in Fig 5.1 by adding the circuit symbol for the missing component correctly connected. So obviously this is a rectification circuit, a half-wave rectification circuit. So the component that is missing is the diode. So I'll quickly draw the diode here. Okay, so there are several ways, but I can start off by doing this. I don't like that line. Better than okay, then finally, okay, so that is our diode. We've connected our diode, which is the component which is needed to rectify. A capacitor C, as you can see, this capacitor here, a capacitor C is shown in the circuit in Fig 5.1. State the effect on the voltage output of including the capacitor in the circuit. Whenever you see a capacitor in a rectification circuit, whether half-wave rectification or full-wave rectification, that capacitor is there to produce smoothing. Okay, so the capacitor is there to produce smoothing, as I wrote there. Fig 5.2 shows the variation with time of the voltage input Vin. Now, as you can see, usually students think that alternating voltage is only sinusoidal. Sinusoidal is like this, follows a sine wave. But that's not the only alternating current. Alternating current is in two parts, but mainly one component is what makes us call it alternating current. Its ability to change direction. That's what makes it alternating current. Even though sinusoidal sometimes also changes their magnitude whilst changing direction. But what makes it alternating current is the changing direction. So here we have current which is changing direction. As you can see in this region, here is positive, here is negative, positive again, and then negative again. So that shows an alternating current changing direction continuously, an alternating voltage. So it doesn't matter even though the graph is not a sinusoidal curve, it's still an alternating voltage. Okay, so Fig 5.3 shows the variation with time t of the voltage output V out, V out. So this graph now is showing us now the output voltage that is going to come. Now, by basic observation, I believe you can see that, just simple basic observation, it is easy to see that the voltage output doesn't have a negative side. The voltage output only has the positive side, but no negative side. And if you check again here, there were 5 boxes. If we checked out correctly, this, 5 boxes. Here, there are now 10 boxes from here to here. So nothing has changed, because the mistake would be to think that these 2 extra boxes makes this any different. No, these 2 extra boxes are equal to 1 box on top there. Anyway, back to the matter at hand. So what makes us know that this is rectified is because there is no more the negative side, it's only positive. And I can also see that here it is smoothed. Why? because whilst in this part it had a positive up until 0.02, but after 0.02 to 0.04 here it was negative. But in this graph, from 0 to 0.02 it's positive, but instead of becoming negative between 0.02 and 0.04, it actually decreases gradually without even reaching 0. Then it increases again, showing that there's been some smoothening. Smoothening avoids us to having 0 voltage, even though we have removed the negative component. We should do, and the negative component is just negative to show direction. It's not like that voltage is any less in terms of magnitude to the positive voltage. Okay, so determine the frequency of V in of the voltage input. Determine the frequency of the voltage input. That's the question now. Determine the frequency of the voltage input. So how do we determine the frequency of the voltage input? We just go back to the voltage input here. We need to find the period, because there are a few ways of finding frequency, and in alternating currents we can find frequency by saying omega is equal to 2 pi f. So if we knew the angular frequency, then we can find the frequency, or we can find the frequency by simply knowing the period. That's it. So that's our thought process there. So the question is, how do you find the frequency? You must find the period. So period, we must check 2 consecutive points when it is about to do the same things again. For example, here we're at a peak here, then still peak, then goes to negative peak, then here goes again to the positive peak. So this corner here and this corner here show corners that are in phase. So in each case we can say that the time from one such corner, which I will label A, to this other corner, which I will label B, that time is our time period. So our time period is 0.04. So knowing that our time period is 0.04, we come here and then we say 1 divided by 0.04. What is that? That's 25 kilohertz, which is our frequency. Then we go further. Show that the time constant for the discharge of the capacitor through the resistor is 0.038 seconds. So they want us to find the time constant. So we could have found, of course, by saying, okay, we know that the equation for the time constant is equals to tau is equals to CR. Now, we don't have actually the value of the capacitance, even though we have the value of the resistance. So this itself will pose a dilemma on the fact, how do you find the time constant if you don't have the capacitance, if you just have the resistance? So instead of finding the time constant that way, we then decide, okay, we can't find time constant that way. So how do you find the time constant? Then we have to use our graph and what we have on the graph, especially on the discharging of the capacitor. You see, the capacitor, we know the time that it is discharging, and we have a graph of a discharge, voltage discharge of the capacitor. How do we know that we have it? Here, the voltage, if there was no capacitor, the voltage was supposed to be 0. So in this case, this voltage, which is there, the entirety of it is due to the capacitor. So we can actually know that from this time 0.02 to a time of 0.04, a capacitor was discharging. So a capacitor discharged from 0.02 to 0.04. Not only did this discharge, it discharged also from this voltage to this voltage. Now this is, so we have time of discharge, we have initial voltage, we have final voltage, initial charged voltage and final voltage. This alone is enough information in the topic of capacitance for us to be able to deal with this topic. So what do? We say, okay, so we have a point here. What is the voltage at this particular point? If they are from 5 to 2.5, from 7.5 there is 2.5 units. So each box represents 0.25. So 2 boxes represent 0.5. So this here is 5.5. What about here? We would say from 2.5 to here, there are 3 boxes. 3 times 0.25, that's 0.75. 0.75 plus 2.5, that's 3.25. So the final voltage after 0.02 seconds from the time we started to discharge is 3.25 from a voltage of 5.5. So this is the equation that we will use. The equation says the voltage after a specific amount of time, where RC here is the time constant, where V0 is the initial voltage, then this voltage is the voltage that we have if a capacitor is discharging. So, and the RC is the time constant. So instead of wasting our time, we are looking for the time constant. Remember, we just put time constant there, tau. We put the time taken t is 0.02 seconds, and that's the time taken to move from an initial voltage of 5.5 to a final voltage of 3.25. So then because we want to find tau, but tau is contained in an exponential, we use logarithms both sides, because it's only the logarithm, the ln logarithm, which is able to remove the exponential. So we first of all divide both sides by 5.5 and then use the logarithm on both sides. This will remove the exponential and we are left with ln 3.25 over 5.5. Then we make tau the time constant subject of the formula. We say minus 0.02 divided by ln 3.35 divided by 5.5. When we do this, it will give us 0.038. We have found our time constant. Okay, so if we find our time constant, then the next question says calculate the capacitance of C. Give your answer with a unit. So the capacitance of C, what do we do now? We already know the resistance and we now know the time constant. And even if you had not worked the previous question, you have a habit of not jumping questions, because knowing the time constant, knowing the resistance, which is given as there as 1.4 kilo ohms, this is enough data for us to find the capacitance. It's a free mark, this one, ultimately. How many marks are there here? There are 2 marks. So there are free 2 marks there, even if you had failed the previous question. So we make C subject of the formula, we substitute the time constant, we substitute 1.4 kilo ohms, our resistance, we find this answer 2.7 times 10 to the power minus 6 farad. So that's the unit of capacitance. Now the question then says, the circuit in Fig 5.1 is modified so that it provides full wave rectification. Now you must understand that full wave rectification means that we no longer have either the negative component of the voltage. We have removed its negativity such that it is now all of it going in the positive direction. So instead of voltage changing direction, there's no more changing of direction. So the question asks, suggest with a reason how V out, the voltage output, now varies with the time when V in is as shown in Fig 5.2. So if the voltage input is as shown in Fig 5.2, this is Fig 5.2, and that's the voltage input. So if we rectify such that there's no more the negative side, now the negative side, unlike in half wave rectification where the negative voltage was being made 0 during that part, for example, during this part from here to here, it will be 0, then it becomes positive again, then it will be 0 here in that region. In full wave rectification, it's not made 0. It's actually made to go in one direction as the direction. So the direction is made 1. So this means that this part, which is supposed to be negative, instead of being negative, it will actually go in the positive direction like that. Let me use a black color so that I show the effect. So this part will go like that, and this part will go in this direction. So what does it mean? It means that we have a voltage, constant voltage throughout. We have a constant voltage. In fact, let me use a red color to show that we have a constant. Constant voltage throughout. Why? Because wherever it was supposed to be negative is now positive. But since the voltage input is of same magnitude despite changing direction, it means that if it is now going in one direction, then even when it was supposed to go in the opposite direction, it is now going in the positive direction with a constant magnitude, with the same magnitude as the one which is supposed to go in the positive direction, meaning that we have a direct constant voltage there. So this is what we should write in our answer. V in has a constant magnitude in both positive and negative, as I showed you. V in had a constant magnitude in both the negative and the positive. It had a constant magnitude of 5.5. So it was either 5.5 minus 5.5. So V out is now constant. Why? Because V out is the rectified output and it's been full wave rectified, meaning that there is no time when it is zero. The negative side is not cut off to become zero. The negative side is actually made to become positive when it is going through the output. So V out is now constant, as I showed, and it does not vary with time. I hope that is clear.